So today I want to just say a few things about HSQC experiments, but then start talking about relaxation for the rest of the week. And then next week, Ann will introduce tensors. So the COSY is the start of 2D NMR and the most basic NMR experiment, 2D NMR experiment for homonuclear systems. And either the HSQC or the HMQC are the basic 2D experiment for heteronuclear NMR. So here is the simplest HSQC experiment. And one of the main things in looking at pulse sequences is learning how to break them into blocks that you already know. So I've helpfully color-coded then for you the sequence in 3 blocks. And in the problem set, you've worked out, hopefully one of the problem sets, you've worked out what happens with chemical shift evolution if you put a 180-degree pulse in the middle of an interval. What happens if you put a 180-degree pulse on the other spin, and what happens if you put on 280-degree pulses. So if we look at this first block, for example, we know the first 90-degree pulse is going to generate minus IY magnetization. And during this first time period, tau, 180-degree pulse tau, what will happen to the I-spin chemical shift? That's an echo. So the I-spin chemical shift is going to be refocused. So I don't have to do any calculation for that. Now, what happens to the J coupling? I have simultaneous 180-degree pulses on both spins. I don't remember the problem set. Anybody online?
Yes, I'm here.
So what do you think?
Huh?
In the first gray block, if I apply 180-degree pulses on both I and S, what happens to the scalar coupling? Does it refocus or does it evolve?
Not sure exactly what will happen, but I'm looking at the Z magnetization. No, I'm not sure exactly what will happen.
So you should look back at either problem set 1 or problem set 2 where you work these all out. And there you would have concluded, hopefully, that if we apply a 180-degree pulse to both spins, the J coupling is unaffected. So the J coupling evolves for the whole time period. One way to think about it is to think about the pulses acting on the Hamiltonian. So chemical shift, Hamiltonian is omega IZ. A 180 turns IZ to minus IZ. So the chemical shift is going to refocus after the 180-degree pulse. But the J coupling, the Hamiltonian is pi J 2 IZ SZ. And if we apply a 180-degree pulse on both spins, the Hamiltonian is unaffected, so the J coupling is going to go on. So we'll have the J coupling evolve for a total time period 2 tau. And if we adjust 2 tau appropriately, then the minus IY will become plus 2IXSZ by our rules of the product operators. And then we apply a Y pulse on the I spin, and we're going to end up with 2IZSZ at the end of the first block. And by recognizing the spin echoes, I don't have to do a lot of calculation. And this assumes that I adjusted the delay so that 2 tau is equal to 1 over 2J, so that the modulation of the coupling, which goes as sine pi JT, the sine term is maximized. So then tau is 1 over 4J. So the 2 tau is 1 over 2J. Then I have the second block. So this first pulse, if it's X, is going to turn the SZ into minus SY. So I'll have transverse coherence on the S spin. And now I have this time period, T1 over 2, a 180, T1 over 2. First of all, are there any pulses on the S spin? No. So the chemical shift is going to evolve for the S spin for a total time T1. But there's a 180-degree pulse on the I spin. So what's going to happen to the J coupling?
Is it going to cancel out?
It'll refocus because if we think about what happens to the Hamiltonian, the 180 on the I spin will turn IZ to minus IZ, so the Hamiltonian inverts, and we'll get refocusing. So here we'll get chemical shift evolution of the S spin, but we'll refocus the J coupling. Do we have to worry about chemical shift of the I spin? What's the I spin operator during this period? Right, this first pulse creates minus 2 IZSY.
It's always on Z.
It's always on Z, so we don't have to worry about the chemical shift evolution here. So we already know what our second dimension is going to look like. It's going to have the S spin chemical shifts, and the scalar coupling won't appear, so we'll have singlets rather than doublets. And then if this last pulse is X, it's going to turn any term that's SY back to SZ and leave any term that's SX alone. So we ended up with a term 2IZSZ that's cosine modulated, and then 2IZSX that's sine modulated with the chemical shift frequencies. And now we apply an X pulse on the I spin, and then we have another period, tau, a pair of 180 tau. What happens to the chemical shift of the I spin?
Go again.
It's another echo. So the chemical shift of the I spin is refocused. What about chemical shift of the S spin? Because we have a transverse S operator. It also refocuses. Right? There's a 180-degree pulse on the S spin in the middle of the period. So if the chemical shift Hamiltonian was omega sub SSZ, the 180 turns SZ to minus SZ, and we expect to see an echo. So no chemical shift evolution of either spin during this period. And what about the J coupling? We have the 180 on both spins. Nothing, the J coupling will evolve because we're going to invert IZ to minus IZ and SZ to minus SZ. And the Hamiltonian is pi J to IZ SZ. So the pair of 180s leaves the scalar coupling alone, and we'll get evolution. And again, I'll adjust 2 tau to be equal to 1 over 2J. So I'll convert. So after this pulse, this term becomes 2IX or minus 2IYSZ. And if I adjust the delay properly, that will convert to this becomes minus 2IY. This will convert to 2 or convert to IX. Right? The antiphase term will become in phase, and there may be a sign error. What about this term? After the pulse, I'll have 2 IYSX. What happens to that term under the J coupling? It's unaffected because it's zero and double quantum coherence. And zero and double quantum coherence don't evolve under the J coupling. We looked at that because the 2 energy levels move up together or they move down together in the presence of the J coupling. And so we end up then, before acquisition, with 2 terms. Here, in this dimension, in the T1 dimension, we're just going to get a singlet at the omega S frequency. IX will turn on decoupling so that we collapse what would be a doublet. We'll collapse it to a singlet, and X is in phase or absorptive, an absorptive signal. So we have absorptive line shape. It would be an in-phase doublet because we're going to collapse the coupling with the decoupling seat. We'll have singlets. What about detection here? What kind of signal do we get?
No direct signal.
Right, there's no signal because it's zero and double quantum coherence. So we just have this signal. Now, of course, the Fourier transform of the cosine has the usual problem that that's going to give 2 signals, one at plus omega and one at minus omega. So we have to get quadrature detection, and we'll do that usually by changing the phase phi 1 here from X to Y in order to pick out a sign modulated term. So you can do that at home. You can go through this calculation with this being a Y pulse, these two being Y pulses, and show that you'll end up with the signal that goes as sine omega ST1. So that then, having taken two experiments, we can combine them into a complex pair and get a Fourier transform with only one peak. The other elaboration here is what happens with something that isn't attached to the S spin. Let's just have a hydrogen that isn't attached. So after the first pulse, let's just look up here, we have minus, let's call it R, minus RY magnetization. There's no scalar coupling and there's no chemical shift evolution. So we still have minus RY magnetization. That's not affected by the pulse. So we have minus RY magnetization. No chemical shift evolution here because this is an echo. So we stay minus RY magnetization. This is an X pulse. This will put minus Y on minus Z, and then a 180, and we're back on plus Z. So in principle, in this sequence, something that's not coupled to the S spin starts on plus Z and ends up on plus Z, and we don't see it. In practice, if that's a very strong signal, this isn't going to be perfect. And we're going to have some residual magnetization somewhere from V1 inhomogeneity, whatever, that we might want to get rid of. And if we're doing this at natural abundance, we're going to have tons of such magnetization. So the other thing that usually gets done with phi1 is to change the phase from X to minus X. And what effect will that have? Well, if this pulse here is suddenly minus X, that's going to change the phase after the pulse from minus Y to Y. So both of these terms are inverted. And at the end of the day, our first experiment was minus IX. The second experiment is going to be plus IX. And then we subtract them with the receiver phase cycle. So the signal we want adds up. But of course, our R spin knew nothing about the phase of the S pulse. So we'll end up canceling magnetization from spins not attached to the S spin. So that's a kind of phase cycling. We could analyze it with the phase cycling theory that we developed, but it's so simple, people hardly bother. You know that if you change the phase of the pulse on the S spin by 180 degrees and subtract the two experiments, you're going to cancel all spins that don't know about the S spin. It's rare that we have to worry with the heteronuclear experiments about phase cycling for multiple quantum coherence, etc. So that's a big simplification. So the take-home message is going to be, as we start to look at more complicated pulse sequences, your goal is to first divide them into these blocks that you recognize what's happening, so that you don't have to work out every possible product operator, right? There's no point in working out the chemical shift in this gray block because you know it's going to refocus. there is an HSQC ubiquitin. And I think, hopefully I mentioned last time that the way we acquire the spectra, it looks like the edges are connected into a cylinder. These red peaks here are the arginine and epsilons. They're actually up around, I don't know, 84 parts per million. So they're off the top of the screen in reality, and they've wrapped around and reappeared from the bottom because the edges are connected. So if the top edge is, I don't know what it is, let's suppose that the top edge is, like it's maybe 100 parts per million. If these arginines are at 80, let's say, then they're 20 parts per million above our upper edge, which means they should appear wrapped in 20 parts per million in from the lower edge, because they just wrapped around, and that looks approximately right here. But they happen to be upside down. Red is upside down. And that's because this spectrum was acquired with the first point being set to half the sampling time, which means 180-degree phase shift had to be applied. So that means that these red peaks, they should have gotten the phase applied to them as if they were at 80 parts per million, but instead they got the phase applied, or whatever this edge is, minus, or this edge minus 20 parts per million. And it turns out when you work out the arithmetic, that'll mean that they're exactly inverted. So if you sample with half a dwell, half a sampling, half of delta T1 in the first point, peaks that are folded are upside down. If they fold twice, they'll be back right side up again if they go around twice. So sometimes this is useful for finding peaks that are folded. On the other hand, it can be not useful if these peaks are near regular peaks, because then the negative lobes start to interfere with the positive lobes of your real peak. If the first point in T1 is adjusted to be 0, then the folded peaks all have a be positive, because then there's no first order phase correction. So depending on how you set the experiment up, you can arrange to have the folded peaks either upside down or right side up. That's kind of up to you. These peaks up here are the side chain amide groups, the azins and glins. And you can see they all have a little shoulder on the upfield side. What's the shoulder? So the side chains are NH2s. What do we put in the sample for the lot? D2O, so there's 5 or 10% D2O in the sample.
That's important. Is it important? Protons?
So that's when one of the protons is exchanged for a deuteron, so that you have an NHD, and there's an isotope shift on the nitrogen chemical shift caused by the deuteron rather than the hydrogen. So the nitrogen frequency is a little different. for the NHDs. What about the ND2s? So here, the big peaks here are the NH2s. The little peak are the NHDs. Where are the ND2s? There's no way for us to get a signal from them because we started with proton pulse. So they're there, and we could go find them if we wanted to by doing deuterium NMR. The lines are probably terrible, but they're there.
The NH2 piece of it, they have this situated in that.
Yeah. And of course, that means that also, 10% of the backbone amides are NDs. So the signals we care about here, the backbone amide signals, they're all 10% smaller than they otherwise would be. So as spectrometers have gotten more sensitive, you can get away with lower levels of deuterium in the sample in order to gain back a little bit of the lost sensitivity from the NDs. And occasionally, people use concentric NMR tubes so that the D2O is a thin film between the two concentric NMR tubes, and your sample has no D2O at all. So for some relaxation experiments, that's important because the relaxation properties of ND are different from NH. And if you're exchanging fast enough, then you end up with some averaging. It'd be hard to take into account in theory.
Does this also happen to cardio? Like, what about like the methyl? See?
Well, the exchange with solvent is very slow for carbonates. But if we grow, so frequently we would grow, or not frequently, we could grow E. coli on fractional D2O and H2O, and then get a distribution, say in the methyl groups of CH3s, CHD2s, CH2Ds, and CD3s. And the CD3s you don't see, but then you would see peaks for the CH3s, the CH2Ds, and the CHD2s. And then by appropriate adjusting of the delays in the index, we could pick out which one of those we actually wanted in the spectrum. It would be sometimes more common today if we knew we wanted, for example, CH2Ds, to just use precursors in the E. coli biosynthetic pathway that we can feed that are labeled in that way that then go directly into the methyls. So for proteins, so-called ILV labeling is a way of labeling isoleucine, leucine, valine with specific labeling patterns for the methyls because you can buy the precursors that have that labeling. But sometimes still we do. And that has the advantage you can get essentially 100%. Whereas if you grow on, say, 50% H2O, 50% water, you're going to get a statistical distribution of the different isotopomers, and none of them will be fully populated. But we still do it both ways sometimes. So this pretty much just says what we talked through, the we have a bunch, we recognize spin echoes, various spin echoes for the chemical shifts. So we don't have to calculate the effect of those chemical shifts, and the transverse two spin operators are multiple quantum, and we don't detect them. And that's just written here, and this is just to remind you what I said. If we look at the energy level diagram and calculate then, for example, the energy in going from alpha or beta to alpha, and take the energies, including the scalar couplings, we see that all the scalar couplings cancel. And we just get back the chemical shifts, so the J coupling doesn't affect the energies, and therefore doesn't affect the frequencies.
Oh,
Mm-hmm.
so you have like in your sample, two sets of nitrogen proton bonds that have very different J couplings.
Mm-hmm.
If you want to, they appear same structure, or as long as you adjust the delay, you can select for which J coupling.
Well, that depends, right, on how different they are. So, for example, in problem set 3, and I'm going to, by the way, modify problem set 3. I'm going to add another problem to it, but I'm still trying to make sure I know the answer before I post it, but I'll post it later tonight. Where you're there building up HNCO experiment, and the coherence transfers then in the beginning are just the one bond couplings. But it turns out there are scalar couplings across the hydrogen bonds that are quite weak. So you can adjust you can adjust the delays so that you evolve the weak couplings, but the strong ones will refocus. It is possible to adjust the two delays more or less by accident that multiples of one are equal to the other. In the case of, so you'll do that in the problem set. That's kind of an extreme example because they're so different. In carbons, the scalar couplings between a carbon and the attached hydrogens depend on whether it's methine, methylene, or methyl. So the number of hydrogens attached to a given carbon affect the coupling constant and whether it's an aromatic carbon or not. So the couplings in a methyl group are about 125 hertz. In the C alpha, they're more like 140 hertz, and the aromatics are even larger. So then it's hard to pick one. They're not so different that you can manipulate them easily independently, but it's hard to set them, find a delay that's good for all of them. There's compromise. You have to make a compromise. There are pulse sequences then that try to make the evolution more broadband to kind of solve this problem. But they're inevitably longer, so relaxation becomes a problem. So they haven't been used a lot, even though we've published a couple papers on them. So we wish they were used more. Now, after we talk some of our relaxation, we're going to come back and look at a lot of pulse sequences. But you should work through this one some more on your own. because this will help you get started on the problem of building an HNCO, because essentially one's going to replicate these kind of blocks. And the next step, if I is hydrogen and S is nitrogen, then once you get coherence transferred to nitrogen, to get it from nitrogen to the carbonyl carbon, there's another set of blocks that look the same, except that the delays have to be adjusted because the scalar coupling constant is different. So these kind of blocks just get replicated over and over again, adjusting the delays appropriately. But I want to switch and get started a little bit on relaxation. And somewhat unhelpfully, we're going to start with relaxation lecture 2. And then come back for relaxation lecture 1. I'm not entirely sure how that happened. But one of the, let me get rid of it. So, because mostly I want to start here to introduce some simple concepts about relaxation, then we'll move on to more complicated ones, but also to talk some about Boltzmann equilibrium. So, restoring Boltzmann equilibrium requires, for example, flipping a spin from alpha to beta, in which case we need some energy, or flipping from beta to alpha, in which case we need somebody to accept energy. And somehow this has to happen in such a way that we get to Boltzmann equilibrium. And this has to do with the fact that the spins are embedded in what's called the lattice in NMR. The lattice is all the other degrees of freedom other than the spins. So it's could be vibrational degrees of freedom, rotation and solution is a big effect, but everything else. And one imagines that the lattice is very big and that it's always in Boltzmann equilibrium. And it can accept, also has a quasi-continuous distribution of energy levels, and therefore is capable of providing whatever energy is needed to go from alpha to beta, or it can absorb whatever energy is emitted in going from beta to alpha. So it's basically a huge heat bath with any amount of energy available. Now, I'm just going to write that we have some rate at which the spins flip from alpha to beta, that I'm calling W minus because we're going from alpha to beta. And that means that somewhere in the lattice, there must be a matching transition going down from some upper level to some lower level. And all this fuzziness is meant to mean that there's plenty of levels available. And here, if we have a transition from beta to alpha, which I've called W plus, then we must go from the lower level to the upper level. And this means that W minus and W plus can't be identical to each other. It must mean that this is a little more probable going from beta to alpha because there's more spins in the more states here. We don't know if these are spins or rotational degrees of freedom, but in the lattice, if the lattice is at Boltzmann equilibrium, there's always more population in the state I called L than the state I called U. We said the lattice is so huge that it's always at Boltzmann equilibrium. So the fact that going from beta to alpha takes some state from L to U has a negligible effect on Boltzmann equilibrium. So if there's always more states here, it must be more probable to do this than to do that. And that means that W plus must be larger than W minus. Yep.
When we say that the lattice is in Boltzmann equilibrium, we mean that there are more states accessible to the system in lower energy compared to the.
Right. And it's so huge that nothing we do to the spins is going to affect the thermal equilibrium of the lattice. So, for example, if this can't be completely true, but suppose I have a 180-degree pulse on the spins, and then when it comes back to Boltzmann equilibrium, there must be, after the 180-degree pulse, the beta spins are inverted. There's now more beta than alphas. And as I recover, there must be some energy going into the lattice. So the lattice should be heating up, but it's so big that I'm ignoring the fact that it's heating up. But that's a negligible effect. In principle.
Hello.
Yep.
A quick question. Like can this that you explain about lattice and I mean, can it in any way cause transition of beta to alpha or alpha to beta, resulting in no signal in NMR experiment?
So hold on to that question for 1 second. Well, let me say a few more words and then answer that question.
Okay, thank you.
In principle, right, I should be able to put a thermocouple into the NMR tube, do a 180-degree pulse, say, on the water, and then watch the temperature of the water change as the water spins relax back to Boltzmann equilibrium. And in fact, people have done that. It's ridiculously difficult because the amount of energy in the spin system is, I think you calculated this in problem set 1, it's a tiny fraction of KT. So you're measuring infinitesimal changes in energy in our 1 millimolar of protein, say, that's getting dispersed into all these other degrees of freedom. So, while yes, we're depositing energy or taking it out, the lattice is just huge compared to the nuclear spins. And the amount of energy in NMR is so small. I suspect it's probably been decades since anyone thought it was useful to measure the temperature change. So actually, you see temperature changes all the time, of course, when you turn on pulses. That has nothing to do with the spin system. That's the electric field that's generated in the coil, heating up the water, because these are, close to microwave frequencies, and a microwave heats up water very efficiently. So in solid state, people try to design probes that are so-called E-free, where the field is largely magnetic and the E field is minimized in the coil, which means it's maximized somewhere else we don't care about. Or in a solution probe, there are coils that are designed so that the E field is roughly orthogonal to the B field, and then you don't use a round NMR tube, you use a tube that's flat, so that the narrow dimension is feeling the E field, and the long dimension is feeling the B field. So there's less water for the E field to heat up. And I mean, that also tells you something about NMR, because we talk about the radio frequency pulse, but we don't really have electromagnetic radiation in the way you think of it. Electromagnetic radiation that's coming out of the lights here, the B field and the E field are equal to each other. They're just oscillating out of phase and orthogonal. But we're working on dimensions much smaller than the wavelength of the radio frequency field. At 500 megahertz, if you sit down and do the calculation, the wavelength is, I don't know, a few centimeters. So the dimensions we care about of the sample are much less than the wavelength, which would be called near field. When you get to this behavior of a classical electromagnetic wave with oscillating B field and E field components, that's called the far field. And in the near field, things are different, which is why you can think about making something, a coil where the B field is much higher than the E field. You can't do that in the far field. They're then oscillating together. That was a digression. And what was I going to say to answer the question? To answer the question then is, in fact, the flips are happening all the time. So if we have the sample at Boltzmann equilibrium, it's not as if there's a fixed population of the beta state and a fixed population of the alpha state. There's constant flips going on by this process, omega W minus and W plus. So constantly spins are flipping and the lattice is flipping energy states. But at equilibrium, there's balance. So that the flip rates down and up are balanced against each other so that there's no net change away from Boltzmann equilibrium. This is just like a kinetic reaction at equilibrium. When you say I have a chemical reaction at equilibrium, you know that the molecules in the in the reactant and the molecules in the B in the product aren't fixed. They're constantly reacting back and forth. It's just that the macroscopic net rate looks to be zero because the forward and reverse rate are balanced. And if you could look with a fine enough device, right, you would see the fluctuations. And of course, this can be done these days with single molecule spectroscopy, where you can see the fluctuating rates back and forth. So same thing here. If we could look at a small enough volume of sample, we would see the fluctuations between alpha and beta caused by the random flips. But we have 10 to the 17th spins. So macroscopically, we don't see these fluctuations at all. All fluctuations tend to happen on a scale that's the square root of the number of particles. So if, let's say we have 10 to the 16th spins, or 10 to the 18th, let's say we have a really concentrated sample, we have 10 to the 18th spins, the fluctuations are going to be on the order of 10 to the 9th, which means that the fluctuations are 1/billionth of our signal. And we're not going to see that. We have no way of measuring something like that. In order to see the fluctuations, we have to get down to 1,000 molecules, right? In which case, the fluctuations are on the order of 30, or 30 molecules, or about 30% signal. Now we could measure. We have to get down to 1,000 molecules, and we can't get down to 1,000 molecules by NMR. We can get down to 1,000 molecules by fluorescence. So the flipping, so the answer to your question is the flipping between alpha and beta is always happening. It's always happening with the T1 relaxation rate constant. But in Boltzmann equilibrium, everything is balanced. Does that help? So then of course I always know what answer I want. So I'm going to say that W plus is 2 times some other rate constant I'll call W times the population of the lattice in the lower state. And W minus is 2 times W population in the upper state. Because the lower state of the lattice is always higher population, then W pluses are always larger than W minus. And I put the factor 2 in because I know the answer I want. So then W minus over W plus is then just the population of the upper state divided by the population of the lower state for the lattice. But the lattice is always in Boltzmann equilibrium. So if the energy change in the lattice has to be matched to the energy levels of the spin system, I know the energy level of the spin system. This energy difference between alpha and beta is h bar gamma b naught. So that's the Boltzmann ratio of populations in the lattice. And that is approximately, then by first order expansion, h bar gamma b naught over kBt. Okay?
So the W is a constant. It's a survey constant that we don't know yet.
Right. Right. So I'm just saying there that W plus has to be proportional to the population of the lattice state in the lower level, and W minus has to be proportional to the population of the lattice in the upper state. So I could pick any constant of proportionality I want, but since I already know the answer that I want to get to, I picked the constant of proportionality to be 2W. We could have just called it zeta. That would have been fine as well. So then, the good thing about the spins is they're countable. So I can just write a kinetic rate equation, just like you would in chemistry class. So the change in population of the alpha state has to be minus W minus times the population of the alpha state. The minus means I'm losing from the alpha because it's going to beta. And then I gain W plus times the population of the beta state because those are the spins that are flipping from beta to alpha. And then the population of the beta state is just 1 minus the population of the alpha state. So I've written that here, and that says, if I just do the algebra, I get this. And then I do the same thing for the beta state. We gain population from the alpha state, we lose population from the beta state. I do the same little bit of algebra, and I do this. And now I can ask, let's subtract these 2 equations to get an equation for the difference in the populations. And I subtract the 2 equations and do a little bit of algebra and remember what I meant by W minus over W plus, that those are fixed by Boltzmann equilibrium. I get here with some algebra. And now here's that same equation, and I multiply both sides by this factor, and that gives me Z magnetization. I mean, I had been saying that Z magnetization was 1/2 of population of alpha minus beta. But of course, that left off all the constants of proportionality that give us a real number. If you look back in the notes, that was gamma B naught and the number of spins that we have. I multiply by this to change the populations into real magnetizations. And I then see, first of all, I recognize that this was Boltzmann equilibrium magnetization. Again, if we look back in the first lecture, this is Boltzmann equilibrium magnetization. So this says that longitudinal magnetization relaxes back towards equilibrium with a rate constant R1 that is 2 times W. So the assumption that the lattice was in Boltzmann equilibrium eventually told us that we had to relax back to the spin state, reaching Boltzmann equilibrium. And that's relatively close to a fundamentally true description. It turned out the business about Boltzmann equilibrium is quite complicated. So this is close to rigorous. Rigorous enough for us.
The magnitude of mz smaller than m naught here, or
Well, mz would depend what we did to the, so at Boltzmann equilibrium, of course, mz of t is equal to m naught, so nothing happens. But then, for example, suppose I apply a 180-degree pulse, then mz after the pulse is going to be minus m naught. And now I'll start to see recovery as a function of time.
can we say that mz of t is equal than or less than m naught here? Equal to or less than?
Normally, yes, but we have our tricks. Because remember, with the inept sequence, I can transfer polarization from the hydrogen to the nitrogen. So then the polarization of the hydrogen is 10 times larger than the nitrogen. So if I transfer most of that to the nitrogen, then mz of the nitrogen is going to be way larger than m naught. And instead of seeing, usually you think of recovery equilibrium as I turn the magnetization upside down, and now I watch it recover from negative back to positive. But if I do this polarization transfer, what I'm going to see is a huge nitrogen signal that decays down to its final Boltzmann value. So prior to the invention of these polarization transfer tricks, what you said would be true. But now, with the net, we can transfer polarization. And then, of course, with DNP, right, you can transfer polarization from the electrons and have hundreds of times more polarization on the spin than its Boltzmann equilibrium. And it'll eventually just relax back to that Boltzmann equilibrium. Or there's all kinds of hyperpolarization methods, right, that are used, hyperpolarized xenon, etc. So we have ways of making the polarization much larger than Boltzmann, but eventually the relaxation will go back to Boltzmann. And all that energy is out in the lattice somewhere. Now, that was just a single spin. And of course, we could do the same trick for 2 spins. And that leads to what are called the Solomon equations. So of course, now we know we have 4 states. For example, one state alpha beta would be plus a half and minus a half for the 2 spins. And I can draw my usual energy levels. And here are the frequencies and the energies, and here are the populations of the different states. We won't worry about the J couplings. You know, the J couplings are what we're talking about, are very small effects. And now I have a bunch of rates connecting the different levels. Before I just had up and down, but of course now I have up and down connecting all of these levels. And the reality is, of course, I should always have two arrows here. Right? I should have something here that's omega I plus, or WI plus and WI minus, because the populations of these two levels are different. So going down is going to be different than going up. So essentially what I've written is WI, I've taken the average of the two. And that'll be okay for what I want to do today. A more complete description is I would keep these separate and work through what happens. But that's just a lot more algebra. I don't think it's in the note. But then we do exactly the same thing. Here we have the population of the alpha alpha state. We lose population of the alpha alpha state because the alpha state could go to alpha beta, it can go to beta alpha, or it can go to beta beta. And it gains population from beta alpha, from alpha beta, and from beta beta. So I've written that all out. Now, I could go back and do what I just did to figure out that we go to equilibrium. But having already done that, I'm just going to say there must be some constant here, K, that assures me that I go to Boltzmann equilibrium. And then at Boltzmann equilibrium, the differential will be 0. And I can solve for K. And I find for K that it's these rate constants with now the equilibrium populations. And I can substitute in for K, and now I have a differential equation for the deviation of the population from Boltzmann equilibrium, which is convenient. You'll see later that in the full theory, we also have to imply that. Our theory, as we'll do it later on in the class, won't predict the proper recovery to Boltzmann equilibrium, and then we say, aha, we know we have to go to Boltzmann equilibrium, and we fix that in an ad hoc way. So here I have an expression for the deviation from Boltzmann equilibrium of the alpha alpha state in terms of all the other states. And obviously I can do that for all 4 states, and I have 4 differential equations. Now we usually don't work with the population, we work with IZ magnetization, SZ magnetization, etc. So we want to convert these to the magnetizations, and remember that IZ magnetization is going to be proportional to the difference in populations where the I spin is in the alpha state minus the populations where the I spin is in the beta state. So here, the I spin is in the alpha state, here the I spin is in the alpha state, here the I spin is in the beta state, here the I spin is in the beta state. So IZ is going to be proportional to the sum of these two minus these two. Whereas for the S spin is alpha, S spin is alpha, S spin is beta, S spin is beta. So I have to add line 1 and line 3 and subtract line 2 and line 4 to get SZ magnetization. So it's convenient to write this as a matrix to begin with, rather than writing 4 separate equations. And as we go forward in relaxation theory, it'll be lots of matrices. And then I want to turn these into the identity operator IZ, SZ, and there must be a fourth, right? I have 4 equations. If I'm taking linear combinations, the sum of the populations has to be 1, or the sum of the deviations has to be 0. But there must be a fourth thing, and that fourth thing is what we already know is 2IZSZ. So I want a matrix that turns these into these. So obviously the E is easy, I just add them all up. IZ, we have to take entry 1 and entry 2 and subtract entries 3 and 4. SZ, I have to take 1 and 3 are positive, 2 and 4 are negative. And then the fourth line just has to be orthogonal to all the other ones. I don't know a priori what the fourth line of this matrix has to be, but these have to be 4 linearly independent rows. So I just figure out what it has to be, and that's 1 minus 1 minus 1, 1. So I can multiply this by this matrix, and I'll get these new representations. And the reason for doing it this way is in part because we'll do this kind of thing over and over again, but also in part because it forces me to put this fourth line in. I'm starting with 4 things. If I'm doing a linear combination, I have to end up with 4 things. I knew what 3 of them were, and now I'm forced as to what the fourth one is going to be. The fourth one then is P alpha alpha minus P alpha beta minus P beta alpha plus P beta beta. Now, there's no particular reason, if I ignored the rest of the course, why I should call this 2IZSZ. I could have called it walrus, but from the other parts of the course, I know that's what I should call it. So then my new equations look like this. I've taken here, if I want to transform this vector into the magnetizations, I have to multiply by U on the left side. And U is independent of time. So if I multiply by U, I can move it inside the differential. But then over here, I have U times W. I have to multiply both sides. And to get that to something I know, I insert between the W and the column vector U minus 1 times U, because that's the identity. I can always insert the identity. And then, so then I have U, W, U minus 1, and U times the column are just my magnetizations. So my new equation for the magnetizations requires this kind of transformation of this matrix W. And hopefully you see a lot of familiarity to what we've done already. I have a matrix, I have a representation in one basis of the populations. I want a representation in the basis of the magnetizations. the vectors get transformed by multiplying on the left by U, but the matrices get transformed by this kind of sandwich, UW, U minus 1. I just do all the arithmetic, and here's what I find out. I find out that there's a relaxation rate for the I spin. This is R1 of the I spin. And it depends on these rates, these W's. There's a relaxation rate for the S spin. That's its R1. It depends on a different combination of the W's. There's a rate for this longitudinal two-spin order, as it's called, 2IZSZ. And it has its rate that depends on the W's. But then there's something new. I mean, those we expected. All these operators have to relax away to get back to Boltzmann equilibrium. But there's something new that says magnetization is exchanged between the I spin and the S spin. And that depends on the difference between W2, the flip going from alpha alpha to beta beta or beta beta to alpha alpha, and W0, which is the flip flop, alpha beta going to beta alpha and vice versa. So if we come back here and look at the picture, this exchange of magnetization depends on this transition and this transition. So this will only happen, right, if this difference is non-zero. So there has to be a W2 and a W0, and they can't be equal to each other. If they're equal to each other, then we're not going to have any effect either. So this is the famous nuclear Overhauser effect. At least for solution NMR, there's only one process that leads to this, and that's the dipole-dipole interaction between the I and S spin. So if there's a dipole-dipole interaction, that Hamiltonian leads to eventually relaxation rates W, where W2 minus W0 can be different from zero. There's conditions in which it is zero, but there are also conditions under which it's not zero. In this picture, there is no exchange of magnetization between SZ and 2IZSZ. If I went back and put in that WI was really WI plus and WI minus with different rates going up and down, the algebra is much more complicated, but I do find that there are conditions in which there can be cross-relaxation between the two-spin term and either of the one-spin terms. That comes up from what's called relaxation interference that we'll eventually get to, but it requires that there's two Hamiltonians at work. And most common, that could be two dipole interactions. Perhaps our S spin has a dipole interaction with two different I spins. Or it could be two different relaxation mechanisms, for example, chemical shift anisotropy and dipole-dipole interactions. And that leads to Prosy effects. But for now, we don't have that here. We just have R1 for the individual spins, and then a cross relaxation here constant. when Overhauser presented this, he was basically laughed down. This couldn't be the case. So these are sometimes called the Solomon equations. And if we had more spins, we would just have bigger matrix. And the elements would all be have the same kind of form. I think I've said everything on this slide. So for two spins, if we ignore the two spin order, which is doing its own thing, it's not cross-relaxing, we just have this 2 by 2 matrix, and we can ask Mathematica to solve those differential equations. So here's the solution. Not that we particularly care about the numbers, because we're mostly going to make graphs. But here's what it looks like in the simple case. If the two R1s are the same, then there's a pretty simple functional form and we can make a graph. So if we perturb away one of the spins away from equilibrium, it will decay and transfer magnetization to the other spin. And if you've seen this kind of graph, it's what people call an NOE buildup. If we have some mixing time in a nosy experiment, for example, you see a buildup of magnetization that's being transferred from the other spin, and then eventually everybody decays away back to Boltzmann equilibrium with R1 rate constants. We'll probably skip through some of this because a lot happens in these experiments with Z magnetization, depending on what you do to the two or more spins. So for example, at Boltzmann equilibrium, right, nothing is happening. Everybody's just exchanging at equilibrium. There's no net change. In what would be called the selective inversion recovery experiment, I invert one of the spins. So now one of the spins starts at Boltzmann equilibrium, the other is away from Boltzmann equilibrium. As this one starts to recover, it's going to be transferring magnetization to the other one. So the other one is going to lose Z magnetization, be perturbed away from Boltzmann equilibrium, and then eventually everybody comes back to Boltzmann equilibrium. So there, spin flips between the two are moving this one towards Boltzmann equilibrium and perturbing this one away from Boltzmann equilibrium. On the other hand, a non-selective inversion recovery experiment, I can invert both at the same time. And now they have to get back to Boltzmann equilibrium kind of simultaneous. Or I could saturate one and invert the other. There's all sorts of combinations. So they all have names: selective inversion recovery, transient NOE, non-selective inversion recovery, decoupled inversion recovery, where I saturate one spin. So it all depends what's going on here. Is this 180-degree pulse selective or non-selective? During this time period T, am I saturating one of the spins or not saturating one of the spins? And then eventually I'll apply a 90 to generate transverse magnetization and see what happens. Just find some pictures. Yeah, so here is, let's see, green, for example, is how we often measure T1s. We saturate the other spin, invert the, say, the nitrogen, saturate the hydrogens, and then the math that I skipped over that you could look at would say that the recovery is single exponential And we come to a steady state because we're saturating one spin. We don't come back to real Boltzmann equilibrium because one spin is always saturated. So we come to a steady state value that depends on the NOE and the R1. Let's see. Black is the selective inversion recovery. So we inverted one spin, it recovers. This is now bi-exponential because it's transferring magnetization over to the red spin. The red spin started at Boltzmann equilibrium, it loses magnetization, but then eventually R1 takes over and recovers back to Boltzmann equilibrium. And if we fit the black curve, we would see that it's two exponentials. It has a contribution from its R1, but also from sigma, the cross relaxation. And blue is the non-selective inversion recovery. And you can see it's also bi-exponential, but you can also see the recovery is kind of slow because both spins are upside down and they can't mutually flip each other the way they can if one is up and one is down. So the recovery is inhibited. And this can be a big problem in solid state NMR. Because if you flip everybody up in upside down in solid state NMR or saturate everything, there's very, very few spins around that cause the spin flips that would start to get recovery going. So you can end up with what looks like a non-selective inversion recovery that's extremely slow. Even if you did selective inversion recovery, that would be quite fast. Because selective inversion recovery, there's a huge bath of spins at Boltzmann equilibrium available to do spin flips. So it's one reason, for example, when I said we sometimes frequently will deuterate a protein and then back exchange the amide hydrogens. But frequently when we do that, we don't bother with deuterated glucose. So there are protons in the sample from the glucose that the bacteria are growing on. And it turns out that the deuteration at the alpha position is quite high, but not so high at the methyls. So there's still some methyl proton magnetization around. And usually we're happy with that because that means if we saturate the nitrogen, the amide hydrogens, there are methyls around to help spin flip and get recovery to Boltzmann equilibrium. A recovery to Boltzmann equilibrium is how long it takes before we can start the next scan. So if we use deuterated glucose and really deuterate everything, then if we saturate the amide hydrogens, say with even just a 90-degree pulse equalizes the levels, the R1s might become extremely long on the order of 8 or 10 seconds. Whereas normally we're used to recycling between 3 induction decays in 1 or 2 seconds. If suddenly it takes 8 or 9 seconds, that's a huge lengthening of how long it takes to do the experiment. So unless there's a good reason to really deuterate all the methyls, and sometimes we have to, having some protons around to help get around this non-selective inversion recovery problem can be a big help. Let's see.
I have a question.
Mm-hmm.
In that graph, what is the difference between blue and green again? Is like, why doesn't that how does decoupling?
So green, we've saturated the other spin.
Oh.
Right? And that has, since it's always saturated, that modifies the equations. If we went back, let's go back and just look at. This actually is, yeah, from here on, these should all be deltas still. The difference from Boltzmann equilibrium, because here, right, this equation would predict we relax to a fully saturated state. So these all need to be delta equilibrium. So if here, for example, if we imagine that these are deltas, then SZ of t here is SZ of t minus S equilibrium. And if I saturate the S spin, so SZ of t is always 0, then this just becomes minus the Boltzmann equilibrium for the S spin and is no longer dependent on time. And at that point, the solution to this equation, which is somewhere in the notes that I skipped, ends with pure R1 relaxation. That's the only time dependence left. But you go to a steady state, you don't go to Boltzmann equilibrium. I'll have to fix this in the notes. This has been there for a very long time. Otherwise, just like before, I need to add something over here that ensures I get the Boltzmann equilibrium, like I did where I added K, and I could say, put a K here, put a matrix here, a vector here. Set the time derivative to 0 and solve to find out what I had to put there for Boltzmann equilibrium. Or I could say these are deltas. Let's see. Anyhow, you can go through and see all the math, it's all there. Now, we will eventually see that these W's depend on molecular motions at particular frequencies. Right now, we don't know where the W's came from. I just said there are these W's, and we'll need more theory for that. We'll leave that aside for a little bit, but it'll turn out that these W's depend on random motions in the molecule at frequencies that match the energy gaps. And that's probably a good place to stop our first toe in the water about relaxation. So again, you should have gotten an email that we won't have a problem section today because at least some of us have to hustle off to a 3 o'clock seminar. But I'll see everybody tomorrow, and there'll be a posting of a revised problem set 3 later tonight. It just adds a problem on. So if you've already been working on it, you're fine. It just adds another problem. Any questions online? Okay, see you tomorrow.